Good morning. Welcome to the Dallas Schools STEM Environmental Education Center, the virtual field trip. We may not be sorry that you can't be here this morning because it's kind of a cold, wet morning, but we're glad you joined us online. I want to say a special welcome to Joe May Mavericks, to Griner Middle School, to San Wesley Homes, and to Dallas Academy. If you are watching, you have not registered, we appreciate it if you would register with www.tiny.cc/EEC register. That gives us a record of who watched the program. This morning we're going to investigate inclined planes. Introduction to inclined planes is Miss Fuller. Friction on the inclined plane is Miss Nash. Inclined plane investigation is Mr. Broughton. The inclined plane summary is Ms. Ramirez. I'm sorry, I got the wrong programs.
No, this is the correct program. So if you have any questions, please use www.tiny.cc/EEC-question-answer to submit any questions that you have, and we will be happy to answer those. Now we're going to turn it over to Mrs. Fuller, who's going to get us started with that introduction to inclined planes.
Hello, boys and girls. We're going to be talking about inclined planes today. And the people during the Renaissance came up with 6 simple machines. And they are the lever, the wheel and axle, the pulley, the inclined plane, the wedge, and the screw. Now, they didn't call them simple machines. They called them mechanical powers. And because they recognized that these simple machines aided in helping them do work. It's actually the same amount of work, but it's stretched out over a longer distance that makes it easier for us. There was a very famous Greek mathematician by the name of Archimedes, and he said, "Give me a lever and a place to stand, and I will move the world." And he recognized the fact that the lever enabled us to magnify our abilities as humans to move things. So I'm going to demonstrate a real simple inclined plane right now, the ladder. What the ladder prevents me from having to do, I've got a 13-pound box of Arm & Hammer laundry detergent here, and if I'm going to put it on the shelf in my laundry room, I would have to lift it over my head, it's very heavy, and then put it on the shelf. But what the ladder allows me to do over a longer distance, not too long really, only about 3 feet, I can do the same thing, get the same amount of work accomplished by climbing the ladder. And I don't have to lift the 13 pounds over my head. So this is a great boon to people like me that are A, short, and B, not real strong. So let me move this down a little bit so you can see the other thing we're going to do. So there that goes. Okay, so we're going to talk about inclined planes and the different ways that they can help us do work. For one thing, an inclined plane, it's also known as a ramp, simple. It's a flat surface, and it's a supporting surface. And it's tilted at an angle with one end higher than the other, and it's used as an aid for raising and lowering a load, like what I just did with the Arm & Hammer. So this is probably a ramp you're familiar with. That's a little bit too high. Let me lower it a little bit. When you were a little kid, you had your Matchbox cars or your McDonald toys or whatever, and you make little ramps, and you would let them roll to the end of the ramp. And that was a lot of fun. And you could make up little motocross things for your cars, yeah, your Matchbox cars, not your driving cars. And so think about motocross. What are the different ramps that you can think of from that? You've got rollers, you've got downhills. All those things help you increase your speed on your dirt bike in order to make the leaps. So ramps are very important to us. Even when we're kids, they're very important to us. Now, let's see if we can brainstorm different ramps. So give yourself a minute and think about all the ramps you can think of, either at your house or on the playground. Okay, so let's start brainstorming those. First one that comes to my mind are ant hills. We've got fire ant mounds out here at the environmental center, excuse me, in our pastures, and they look nothing more than ramps. And the ants use them to move all their stuff around. The other one would be pyramids. Think of the pyramids, not just in Egypt, but also in Mesoamerica. Excuse me. The Mayans made pyramids, and we even have mounds up here in North America that the native people, the indigenous peoples, built pyramids and big mound cultures. So those are ramps. Slides on the playground. When you go to the water park, you get in those tubes, and those are ramps, just full of water in you, slide you down. I'm sorry. All of our schools have wheelchair ramps so that we can all have access to the parking lot and to the playground. Think about when you go downtown and your parents have to park in a parking garage. That huge road into the parking garage is just a great big ramp. It circles around. I'm sorry. But that's a ramp. Okay, so let's think about circling around. Geometrically, a screw can be viewed as a narrow inclined plane, a ramp, wrapped around a cylinder. And the smaller the pitch, that's the smaller the distance between the threads on the screw, the greater the mechanical advantage. The more work you can get done. And threaded fasteners, screws, hold things together. So let's look at some examples of that. Here's a mason jar. How do you put the lid on? Do you pop it on like you would a plastic one? No. There are threads on the jar, and there are threads in there in the lid. And these threads fit together and screw together, and then you can't pull that lid off. You have to unscrew it. So this is a very excellent way of sealing food inside a container. The next one, think about a light bulb. You wouldn't want your light bulb just stuck in the socket, would you? You want it put on there very, very snugly. Well, look up here at the threads. Can you see those threads that go around? That thread is an inclined plane that's going around a cylinder. The cylinder's the round part of the light bulb. And then this part's the contact, where it makes contact inside the socket with the electricity so you can turn it on. So that's a really good way of putting a light bulb into a socket. Here's another one. Now, if you've been out here and taken a weather lesson, you've probably used something called a vortex machine or a tornado machine. Well, it's got threads on it on both sides, screw threads, and the threads so snugly hold those two bottles together that it prevents any leaks. Now, the other day, Ms. Ramirez was explaining about pendulums and about Galileo noticing them in the cathedral. Well, Galileo noticed a whole lot about the heavens. And another thing he noticed things about were simple machines. And he explained that simple machines do not create energy. They only transform it. They move it from one kind to another. So I believe that is about all that I have right now on the introduction to incline planes, but they help us move things in a more efficient way for us, so that we can pick up heavier things than we normally and move them in ways that we normally could not. If you have any other questions about this, you can ask Dr. Gorman. He'd be glad to answer them.
Thank you, Ms. Fuller. And the question is, what is another example of an inclined plane that we see every day? And when you're going down the highway or even in your neighborhood, lots of times you'll see a pickup pulling a trailer, and on the back of that trailer, there's two steel objects sticking up in the air. And they'll let them down, and they'll drive a tractor up on that trailer, or they'll push a motorcycle up on the trailer or something. And that is the everyday example of an inclined plane. And now we're going to hear Miss Nash tell us about friction on an inclined plane.
Hello, welcome to my classroom. So we were just talking about inclined plane, so just a ramp. So you can make your own little ramps and do some investigations of your own. And you're probably familiar with these, as Mrs. Fuller said, around school. You have a wheelchair ramp so everybody can get in. You have a ramp to get heavy things into the building. And again, it's a simple machine. But if you're thinking about going up that ramp, you need to consider friction. So friction keeps things stationary, things from moving. Friction also stops moving objects. Once they're moving, they don't keep moving forever. Friction will stop them eventually. And there are two kinds of friction. One is what we call static friction, meaning the friction when things are not moving. And kinetic or sliding friction that affects objects once they are moving. And we all know this from daily life, that if we have something, a heavy box, it's harder to get it started moving than once it starts. So static friction, we have to overcome that with what? With force. And things that affect friction are the amount of force, the surface, and the weight of the object. So if we're thinking about the inclined plane or ramp in relation to friction, we need to remember that going up and coming down are both problems. Okay, if you're wheeling something heavy up, you got to push it up. If you're wheeling something heavy down, you got to keep it from getting away from you. So the surface can affect that. Yesterday on the highway, as I was going home, I saw what was almost a bad wreck. The guy came going really, really fast, and all of a sudden he was fishtailing. The back of his car was going back and forth like that. Luckily, there was no one next to him. He was able to straighten out and keep on roaring down the highway. Friction. He lost control of his car because there was not enough friction between the road and tires because it was raining. So the surface can be really important. And on a ramp, you don't want it to be too slippery, right? You don't want to lose control like that guy did on the highway. So if I've got two ramps here, the same, I can change my surface. So I made a little corrugated cardboard, okay, cardboard cover. So convenient. And I've got two little balls here. We're going to test them. And we'll see which kind of ramp surface has more friction. So if I have them at the same height, so the gravity is going to pull them down, the same amount of force on each ball, the balls are the same. I'm going to change one thing, right, for my test. So which one would you predict? Which surface do you think will slow down my little balls? I wonder. Let's see. Okay, so I can do that test a number of times. We always want to run our test a few times to make sure our results are accurate. And indeed, in this case, that corrugated surface slowed it down. So if you were rolling a wheelchair or a big load down that ramp, you would want to have a surface that would help you slow down. Otherwise, it would be hard to roll up and you might your load would get away from you. Now, let's change that. So that one worked out pretty good. Let's try another. So I cut this off my yoga mat. And we use a yoga mat when we do yoga to keep from falling over. So we slip on the floor, but if we have a yoga mat, our feet will stick to it. Bare feet. They stick better. Hold it stick. Yeah. Okay. You want to make another prediction? Same ball, same height, same amount of gravitational pull going down. Here we go. You made your prediction? Let's see. Oh, pretty much even. Try again. So in this case, you can run it a number of times, and they're pretty even. Okay, they're pretty even. So either one would make a good surface. Okay. A pretty good surface. Now we can try different kinds of objects. So if I have, okay, so this is kind of an interesting little demonstration. It amazed me. So I've got two little blocks here. They're the same. And I'm going to put them on my ramp. And they're not going anywhere. Okay. So how can I get them to move? I put them up. So now I've got more gravitational force, right? Because they're higher. But it would be harder to push them up. It's going to be easier to slide them down, right? Okay, let's see, which surface do you think they're weighing? Okay, let me try it again. So it's really interesting to me, in this case, this one actually tends to win just by a little bit. And that's because even though this feels really slippery, and this does too, it's actually microscopically has lots of little imperfections. And at each point they're touching. So this one, because it has that airspace between the corrugation, actually less surface area is touching. So pretty interesting. So you can run all kinds of interesting kind of fun little tests on your own. You can compare different surfaces and different objects. So you can vary the height of the ramp, vary the surface of the ramp, vary what you're putting down the ramp. And it's a fun thing to test and see what you discover. If you have any questions, where did I go? Okay, you can ask Dr. Gorman.
Thank you, Ms. Nash. And the question that came in was, how do you overcome friction? And Ms. Nash just covered that very adequately. All you do is increase the angle of the ramp, or you raise one end of it up higher. That will overcome friction. Now we're going to hear Mr. Broughton tell us about incline plane and springs scales.
Thank you, Dr. Gorman. Let me share my screen here so that we can, whoop. I clicked the wrong thing there. I got to click this one. Okay. Now we're going to do a little better. So I just got to pair my iPad up here with the screen. Almost there. All right. And get my camera turned on. All right. Now you can see I've got an inclined plane here. I'll tilt it so you can kind of see a little better how it's set up. You can see there's a little cart at the bottom, and that cart has a hooked mass piece with a mass of 200 grams in it. And if I pull on this side, the cart moves up the incline plane. But the investigation I want to do is find out how does changing the angle of my incline plane affect the force that is needed to move that cart up the incline plane? And how we measure force is using a tool like this. It's called a spring scale. And you can kind of see, let me get as close as I can to the camera and let it still focus. These numbers on it go from 0 to 2.5, and that is newtons. So the spring scale measures force. There are different types of spring scales that all work the same way. I'll try to hold all of these up here so you can see how the scales work on them. This kind of tan one goes to 10 newtons, the green one goes to 5, and this blue one goes to 2.5. And this is not a very big cart, so I'm going to use the 2.5 Newton spring scale. And let me move this a little farther back so you can see the whole thing happening. And right now, the angle of that incline plane is 10 degrees. I know that because I measured it with this protractor ahead of time. So it is 10 degrees right now. I'm going to hook my spring scale onto the string and start pulling the car up the ramp. And reading that spring scale, it's at 0.7 newtons. So I'm going to record that in my notebook, just like this. So at 10 degrees, the force that I needed to move that cart up the ramp was 0.7 newtons. So let's increase the angle here to 20 degrees by sliding this over. Right there. I'm going to hook my spring scale back on, and now we're going to try it again, but at an angle of 20 degrees. And it is now taking 0.9 newtons of force to move that cart up the ramp. Which kind of makes sense. A steeper ramp is going to be a little more difficult to go up, so it took more force to move that cart up the ramp. Let's try it at 30 degrees. I would say the force that it took to move that cart up the ramp that time was 1.3 newtons. So I'll record that. And we're going to do one more at 40 degrees of an angle. That's a pretty steep angle. And it looks like I'm at 1.6 newtons now to move that cart up the ramp. So I'm going to record that. And there we go. Now I can also graph that information. So I've got a graph set up here. Let me zoom in just a little bit. And you can see the angle is 10, 20, 30, 40. And the force is on the y-axis. So at 10 degrees, it was 0.7. So I'm going to put a little dot. Whoops. Right there at 0.7. And then at 20, it was 0.9. So that dot goes there. At 30, it was 1.3. So that dot goes right there. And at 40, it was 1.6. So that dot goes right there. And if I connect these dots, you can see that as the angle increases, the amount of force needed to move that cart up the ramp increases as well. Now this last column here I have is for work. So the formula for work is force times distance. And the distance that I move that car, if you move it all the way up to the top of the ramp, is 35 centimeters, which is the same in meters is 0.35 meters, and the unit for work is Newton meters. So I'm going to use my calculator here to find out the work that was done. At 10 degrees, it was 0.7 newtons times 0.35 meters, and the work is 0.245 Newton meters. And then at 20 degrees, it was 0.9 newtons times 0.35, because it's the same distance every time, 0.315 Newton meters. At 30 degrees, it was 1.3 newtons times 0.35 meters equals 0.455 Newton meters. And at 40 degrees, it was 1.6 newtons times 0.35 meters is 0.56 Newton meters. So there is my completed table now. So the work also increases if you increase the slope of that incline plane. So that is a quick little investigation you can do using, again, the incline plane, a cart, the spring scale. I guess you would need that protractor as well, which I just dropped on the floor, but there I picked it back up, to measure the angles, to make sure you've got those right. You don't have to have a calculator, but I just went ahead and used one. But that is the incline plane investigation. So I'm going to turn it back over to Dr. Gorman. He'll be able to answer any questions you have.
Thank you, Mr. Broughton. And the question that came in was, where can we get a demonstration kit like Mr. Broughton used to demonstrate the spring scale and the incline plane? And your teacher can go to Dallas ISD, SRC, or you can go to src@dallasisd.org, and you can check out the exact kit that Mr. Broughton used for your classroom. And now we're going to hear Ms. Ramirez give us a summary.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be doing a quick summary of incline planes, and then we're going to go on a virtual scavenger hunt of the EEC to look for different incline planes. So just to review, if we look at our little anchor chart here, an incline plane has a straight slanted surface. So think of examples like ramps. So you guys can make your own simple ramp with a ruler and a bouncy ball, or a ruler and a car, and you can experiment with the different heights of the ramp to see how that affects the car or the bouncy balls. Now, the important thing with our incline planes, like our ramps, is it decreases the magnitude and force needed to move an object, but it's increasing the distance over which that force must be applied. So that's how the incline planes or ramps work. And it's important to note also that the amount of work is still the same. And then another type of incline plane is a wedge. And you're actually going to see me in the video use an example of a wedge, and that is this rock hammer. So a wedge is simply a pair of two inclined planes that move. And there's usually one end that's skinny and then one end that's kind of thick. So examples of wedges would be things like knives, axes, chisels. Those would all be wedges. And then for the wedge, the longer and thinner the wedge is, the greater its mechanical advantage. So wedges can come in all different shapes and sizes. And then the other type of inclined plane is a screw that you guys learned with Mrs. Fuller. So a screw is just an inclined plane wrapped around a cylinder. And so there's different sizes and shapes for our screws as well. And the way the screw works is its mechanical advantage depends on the length of the spiral around the screw and how close together those threads are. So if you've ever examined various screws, you'll notice that the length is different, but also the width between each of those threads is also different. So I'm gonna go ahead and play you guys a little video of what it's like out here at the EEC, and be on the lookout for examples of those three things. So let me share my screen with you guys. desktop and let me get that video going. So what you're seeing here is a trailer aid, and it's apparently used to raise flat tires on the tractor, but I used it for fun with my toy car. Here's a handicap ramp, and I'm pushing a toy car through there. Think about what forces are acting on that car and how's it affecting the motion. Also, why does that car stop at the bottom? And hopefully you guys were able to notice that sometimes the car went faster and sometimes it went slower. So why do you think that is? And I pushed that car several times, and it was interesting to see how sometimes it veered to the left and sometimes it veered to the right. So why do you guys think that was? There's our resident kitty cat, Stripey the cat, investigating what's going on with these cars. Also, the texture of that handicap ramp was different than the other one. This one had a like a gritty texture to it. You can see the lines, versus the other ramp didn't have that texture. So how do you think that affected the motion of the car? And these are some really big screws. I had no idea what they were used for, but apparently they are post hole diggers. So we use them to dig holes. So look at the width between those threads on the screw. This is Jabez, our goat. This is the inside of our Habitat Museum, and you can see a long incline plane, that ramp. So again, incline planes we use to our advantage. A lot of the incline planes or ramps that we have here, we use them to help people walk down areas, especially if they're in a wheelchair. This is showing you guys our aquarium with our fish. Hopefully you guys are able to also notice those stairs. Stairs are also an example of an inclined plane. So think about how stairs make it easier for us to move about. We have a variety of taxidermied animals in that room. This is my rock hammer. When I'm doing this experiment, I'm using safety goggles. That is a geode, and a geode is a spherical shaped rock that's usually hollow in the center, and it has minerals and crystals in it. I am hitting that geode with my rock hammer, and that's what's inside. Hopefully you guys can see that little crystal right there, and it's a close-up of it right here as well. Now, technically, a geode should be hollow with crystal or mineral formations, and those are some of the ones that came out of it as well. Very pretty. I have no idea what it is, but it was super shiny. I was doing research, and there is something else called a nodule, and a nodule is sort of like a geode, but it's more solid. So my question for you guys is to do some research and see if that is actually a geode or if it qualifies as a nodule. So you can do some research on that. So I'm gonna stop this video, and I'm gonna show you something else really quick. So unfortunately, we don't have a lot of slides and enrichment toys for some of the animals out here. So I found just a super quick video of how animals use slides. So we're just gonna look at that really quick. So these are some animals using slides at a zoo. Now you might think, well, why do animals have slides and toys? But that's actually very important for enrichment. So it keeps their mind stimulated so they don't get bored. And these are some super cute goats using a slide or a ramp. Some ducks using a ramp or inclined plane. I'm not entirely sure what kind of wild cats those are. But think about simple things like the banisters and railings that you see on staircases. Those are also inclined planes. So lots of inclined planes that you can find at a playground. This one is a gorilla sliding down a ramp. And then we're going to go ahead and stop it there. And the last thing I want to do with you guys is just a little scavenger hunt. So you saw examples of incline planes at the Environmental Center. You saw examples of incline planes with that video from different people's zoos and backyards. So this one is just a scavenger hunt for you guys. See if you can find at least 2 examples of incline planes. So how are they used to make work easier? So I'm gonna stop our screen share, and then I just wanted to show you guys really quick. This is that, I haven't quite classified it yet. I don't know if it's a true geode or if it's a nodule. So again, try and do that research and see for yourselves what you think it is. But this, I will tell you, was super hard to break open with that rock hammer. It was very solid. So I thought when I cracked it open that I would see a hollow cavity. There was no hollow cavity. It was pretty solid. So this is the broken half pieces. And it's actually, if you do a zoom in, you can see some of the sparkly crystals on the inside. And I found quite a few of these pretty sparkly mineral pieces. They almost look like glass to me, but that's why I put this inside a bag so that I could trap and catch all that stuff that was being flung out. So there were quite a few pieces of these sparkly mineral here, whatever this is, but that was pretty cool. So that was our geode or nodule. Again, you guys can do your research and figure out what this is technically classified as, but I thought that was pretty interesting. So that's all I have for you guys for your review of incline planes. Again, try and go on your scavenger hunt and see what kinds of incline planes you guys can find. We're gonna pass it back to Dr. Gorman, and he's gonna answer any questions.
Thank you, Mr. Maris, for that summary. And the question is, did incline plane do part of the work for you? And the answer is no, it just makes it easier for you to do the work. During this virtual field trip, students discovered that force and motion are related to kinetic and potential and kinetic energy. Students investigated how inclined planes can be used to change the amount of force to move an object. Ms. Fuller gave you an introduction to inclined planes. Ms. Nash explained about friction. Mr. Broughton gave you a demonstration using the inclined plane and the spring scale. And Ms. Ramirez gave you a summary of the inclined plane program. Thank you. How did we do? If you would, fill out a form, www.tiny.cc/EEC feedback, and send it to us. We would appreciate it. Thank you very much for joining us today. I hope you have a great rest of the day, the rest of the year.